Okay, I guess I should make this an official introduction. Welcome, everybody. Um, I'm apparently your teacher, which is a small flex, but it's also not a flex because I don't know really what I'm talking about, and I'm just bullshitting all the way through. But with that said, we'll get started. Today is going to be really simple. By simple, it'll be a long one. I think it's going to be an hour and a half to two. The plan is to go through chapter 10, sort of like we did last time. We're going to go through three chapters at a time. So this will be the last Zoom meeting unless someone can find me an exam at a reasonable time that I can learn and give it to you. If not, then this is the last one, and I wish you the best of luck. That's my preamble. We're going to go through chapter 10. There's going to be, like we did last time, notes, and then I'm going to take some of the things I think that are important and put them on the whiteboard. Sonia and Anisha, I don't know if anybody else here is new. Feel free to interrupt me. I know I can be pretty aggressive. At least that's what Madeline tells me. So Dominic knows that pretty well. So just feel free and let's get started. All right. So chapter 10 is about energy balances and relatively simple. We need to think about an energy balance in steps. It's sort of like a momentum balance, except it's a lot more tricky because energy, as we talked about in chapter 9, is comprised of three major components. It's the heat, it's the momentum, and the convective transport of a system. Luckily for us, if I'm not mistaken, it's the convective transport and the momentum and the work elements of your system that require velocity. If velocity doesn't exist in the system, then our energy is really simply one term, just heat. But we'll get to see that in a second. More importantly, we just need to think of an energy balance, sort of like we thought of a momentum balance. We first select a shell or a slab. It's just a thin little slice that you arbitrarily decide to pick, and you can name it whatever. They say shell, I like slab. We'll go back and forth. So we have to make sure that the surface we're picking is normal to the direction of the heat conduction. In other words, just make sure it's perpendicular to that surface. And then you got to write down your conservation of energy. And I'll zoom in for y'all. I highly suggest printing these out in color. All right, so a steady state energy balance is what we're going to talk about. It doesn't necessarily need flow like last time. If you have flow, it makes it complicated. So let's talk about it in parts. You have the rate of energy via convective transport in minus the rate of energy of convective transport out. We have the rate of energy of molecular transport in minus the rate of molecular transport out, plus the work on the system by molecular transport, minus the work done by molecular transport. Now here, the last two terms are pretty important. So the rate of rate of work done by the system by external forces, that could be pressures, that could be gravity. Pretty much the only two options that'll ever exist. That term is normally dependent on flow. If there's no flow, then there's no work on the system due to an external force. The last term here is the rate of energy production. And the rate of energy production doesn't necessarily need to be anything special. It could be, let's say it's a tube inside a tube that's just producing heat. That's a rate of energy production. It could be a thick piece of electric wire in a tube. That's a rate of energy production. It doesn't necessarily need to do anything fancy, but if something conducts energy, you need to take into account. So
question.
Yeah.
You just scroll up really quick. So it's the rate of energy via. So the first part of the steady state energy.
Yeah, rate of energy via convective transport.
All convective. Okay, and then okay.
Cool.
Sounds good.
Got it. There's common types of boundary conditions. Well, one of the most common is that you can specify your temperature based on the surface you're talking about. It could be at x equals 0, you know the temperature of the surface. It could be at x equals L, you know the temperature of the surface of the outside. That's what boundary condition number 1 is about. The heat flux is another boundary condition you can specify. If you're at the center of an object, you know at x equals 0, there's some type of heat flux. You don't know what it is, but it's a number, and that's important.
Wait, did you say at x equals 0?
Yeah, it could be anywhere.
Okay.
If they don't tell you, you know there's a heat flux.
Okay.
There's flux, so it could be like he did in class. It's like at x equals 0, QR is equal to some shit, but we don't know what the some shit is. It'll be really apparent in a second. At interfaces, the continuity of temperature and heat flux are normal to an interface if required. I'm not sure what that actually means because I haven't seen it applied in any of these questions. But number 4 is pretty important. So if you're at a solid and a fluid interface, so imagine you're at a pipe, and that pipe is surrounded by water, and that water, let's say, has a heat, and then that pipe has a heat. There's a correlation at that. Let's say that the pipe and the water touch at R. So at R equals big R, what is the convective transport to it? You'll say Q is equal to H, which is just a really special term for some constant that relates heat transfer, minus the temperature difference. And we'll see that in a second and in the next example, which I'll modify it and change as I think requires. So we're going to talk about heat being conducted in an electrical wire inside of a pipe. And let me pull up the notes. Boom. So let's get in our brains that we have a cylinder. The cylinder is a beautiful cylinder. She's a length L, just an arbitrary length. And inside that cylinder, there's going to be an arbitrary like wire. And this arbitrary wire conducts some type of heat, which is important. But more importantly, we care about the boundary condition specifically out here. We want to know what the heck this heat wire, this electrical source does to the pipe in itself. We also know that this pipe has a radius of 0 here. And we know that at the outside, it's obviously R equals R. Now, how about the temperature of the outside? We'll call it T naught. Now let's give this sucker a coordinate system. We'll say it's Z coming up. We'll say R is this way. And we'll say that it's theta this way. Like we said in the momentum transfer, you can 9 times out of 10 ignore this, which would be the Y. They don't ever use it, so we'll just go with that. Now, let's make some broad assumptions of our system. There's no flow in the system at all.
How do we know that?
Oh, I'm telling you, there's no flow in the system.
Oh, okay.
There's assumptions based on that. If there's no flow in your system, then V has to be equal to 0. That's very important. Now, there's an electrical conducting pipe. This makes heat. That's important because if you remember what we said earlier, the rate of energy produced is important in this whole thing. So let's say that rate of energy is arbitrarily, this is what the book gives you, just, it doesn't necessarily need to be this, it could just be Q. But we'll say that could be defined as SE. And SE is specifically some random term that's called I squared divided by KE. This isn't really important. It could just be SE for all we care. But since the book gives it to us, we'll play it. And we'll call this the rate of electrical dissipation. Basically, the amount of energy this thing is releasing. 3, there isn't a big temperature rise, so we can assume that the K's are constant. We can keep those constant, so there isn't any differential equations we have to play with that, which is nice. So KE and K are constant since the temperature of the inside and the outside are relatively the same. Okay.
How do you know that, like, so, like, would they be like, how would you know when they would say, like, oh, KC and K are constant, KE?
Well, the problem would tell you the temperature rise isn't big. That's your clue.
Okay.
Okay, cool. Now, let's talk about energy. My fellows that were here last time, the Malaks and the Madeleines, will remember that energy we defined in chapter 9. And energy of any system, X, Y, and Z, is 1/2 rho V squared plus rho H hat multiplied by a V, and this V is a vector, plus tau dot V, this V is also a vector, plus Q. And it'll become a vector once you multiply it by little theta, because this means it could be X, Y, or Z, R, V, and rho, all that shit. So keep in mind, there's no flow. No flow means zero velocity. So what happens to these first two terms?
They go away.
0.
Hey, now we have Dominic and Madeline saying stuff. Let's
God.
go.
Wait,
This is gonna
wait,
be
what is the
Is it
last term? Sorry.
Q. And
okay?
it's
And what's
multiplied.
the thing next by Q? Yeah.
We call that well, this is in the book, they call it something stupid. I'm gonna call it delta. All this means is that it could be QX plus QY plus QZ.
Oh, okay, okay. And then what is that an E at the beginning?
Yes, ma'am. I know you
Okay.
hate my E's.
It looks like a row.
Yeah, you
It's-
make your rows and
I'll make it different for y'all since I'm teaching. Okay. So as Madeline and Dominic used their brains to point out, these go away. So E is literally just Q.
and the
And
reason why they go away is because of all the assumptions that we have. So V equals 0, and
And
then
this assumption comes from the fact that we have no flow in our system. There's no flow anywhere. We'll get to the problem in a second. It does have flow. But does this make sense for everybody?
Oh, show.
For sure. Beautiful. Sonia, Nisha, Malak, ukuleles okay? Toyin?
Good.
Wonderful. Okay. Now, here comes the fun part. Let's pick an arbitrary slice. I preemptively did that, but we'll do this again. We're going to pick a slice that's here. Let's take that slice. From at that slice, we know two things. We know that it's energy obviously being conducted. And we also know that heat must conduct in the parallel direction based on that one boundary condition. Wonderful. So you draw it this way. Q, Q. We also defined in our system that up and down was Z and side to side was R. So
is this still the same problem, or is this like
Yes.
now with flow?
no, this is the same problem. We
Okay,
just took a slice of our cylinder.
Oh, so that's the slice.
That's the slice.
Okay, cool. And it's like, okay, it's going down in the Z direction, technically, right?
Yeah, it's parallel to
Okay,
it. So it's like
cool.
yeah. Wonderful. So Q at R and then Q at R plus delta R. Mind you, the reason there's no other terms is because we already deleted them from existence. So now we have to talk about rates of heat at R and rates of heat at R plus delta R. So at R, we have obviously Q, R, but what is this being multiplied? Being really smart, intelligent humans, you're gonna scream the same thing you scream to me at the momentum balances, and you're gonna say the area, and I'm gonna be like, yes, you guys are so smart. 2 pi RL, that's the area of that surface. And obviously all of this is being at R. How about
that's
R
A plus R, correct?
I'm sorry?
So where you see the A plus R, that's
Where's
A, the letter A.
Or
is
that's
that
a
delta?
delta.
Okay,
Yeah.
thank you. Sorry.
Thank you, Malek. I'm sorry, not everybody's well versed in my horrible handwriting. Madeline is because she looks at the notes I sent
Oh.
you, Dominic.
Yeah, because
Malek,
we're doing the shell balance, right? Right now.
Right.
Okay.
Mm-hmm. Okay. How about at R plus delta R? Do you think the area is going to change? Unanimously, beautiful, because it's the same surface. Now, is QR going to change? Kinda. All that changes is that we're at R plus delta R. Now, ladies and gentlemen, what's the external force on my system? Is there any? There's no flow, so is there?
Nah.
Good. But we did say something else. We need to talk about the rate of heat production. And how did we decide to model that rate of heat production? This bullshit right here, that SE. We do have to take that into account. So normally in your shell balance, you'll write thermal energy. And at thermal energy, you do the volume of the system multiplied by that parameter that is making this energy exist. So in other words, it'll be 2 pi r del RL multiplied. We'll just keep it as SE because I don't want to write I as SE. And this SE is that thermal dissipation. Now, as before, everybody should know this step. We're going to write this whole thing out in this disgusting fashion. 2 pi RL QR at R minus 2 pi RL QR at R plus del R plus 2 pi R del RL. Let's see, what is this all equal to?
0,
Because
because it's in the that thing you showed in 2.1.
there's a simple answer, Dominic. Everything we're talking about is steady state.
Oh, and it's steady state.
There you go, buddy. All right, so we're going to rearrange this and also divide, and hopefully I didn't fuck up the division this time, guys. We're going to divide by 2 pi delta R L. And if we do that, and we're going to rearrange this so we don't get a negative derivative, we're going to write QR R plus del R minus QR at R. Both of these are going to have an R in front of them. I'm just going to factor it out. Divided by del R. Now, Madeline, you're not allowed to answer this. And since we flipped the signs and everything, these two flip signs, this one flip signs, becomes negative. The math checks out. So then you move it to the other side, it's still a positive. Madeline's not allowed to answer this. What do we do to this whole term? What does this look like?
Why does Madeline not get to answer it? This is not her part.
Oh, it's not? What the hell was she saying last time? Oh, you're right. It was you who did this one. I'm sorry. I don't have faces when I see this. Okay, Malak can't answer this one. Anybody else is free game. What does this look like to you?
A derivative.
Ah, yes. Remember, in Calc 1, it's called the first derivative. That looks beautiful because you have a del R in the bottom. So we take the limit of this as R approaches 0. We get a beautiful looking derivative. dr RQR. And it's all still equal to SER. Now, Malak,
Wait,
since
could you go
have
back? Sorry. So what you have written right now is R. So where it's right next to the limit delta R equals 0. So it's R parentheses QR, and then the line 1 plus delta R. Why is it 1 plus
R,
delta R again?
It's R plus delta R.
Okay. Why is it that now?
Because what we did was to avoid the negative signs and to avoid a negative derivative from appearing, I flipped the signs and everything. This became minus, this became plus, this became minus. Then I
Okay.
rearranged it. And then added this to the other side. And now we have these in the order where it won't give you a negative derivative. And we like to live in the world without negatives, right?
Yeah.
Does that make sense, Dominic?
Give me a second. I think so. Then yes.
Beautiful. Anybody else with questions? Oh, wait.
Wait, could you also
Remember-
scroll up one more time? Okay. I think I'm good.
You good? Nobody else? I know I'm a little feisty. Wonderful. Okay, let's get this party started. So we took the limit and we ended up
Wait,
getting this
I'm so
beautiful-
sorry. Go back. Why do you divide by delta R again? Because or like the two pi delta R? What? Because when you look at the like the equation where you have the minus plus minus whatever, you don't have a delta R. Do you just assume?
Delta R is
that-
right here.
Oh, okay. Sorry. Thank you.
I know, Dominic, my handwriting's terribly. I'm gonna rub it in. Okay, so, okay, this is the time Madeline doesn't get the answer, so I guess I'll throw it to Malak. What do I do? This is an ordinary first order differential equation. What do I do?
Integrate.
Wonderful. You gotta say it with the same passion Madeline said. So sad. So once
That
we
is the
integrate
same
this,
I'm not Madeline.
I know. QR.
Integrate.
There you go,
So-
lady.
So do you,
So,
how'd you get the dr over there? Did you just multiply it from the bottom to the top?
so when you take an integral, you have to have an integration factor. And since we're integrating a differential equation with dr, you had that dr in there to make this make sense. Cool.
Okay.
So r, this derivative and this integral, they cancel. You get rqr se, and we're all engineers, it shouldn't be too difficult. R squared over 2 plus c1. Okay, we're almost there. Let's get our qr by itself. Qr is equal to ser divided by 2 plus c1 over r. Wonderful. So we're
Question.
almost home.
Is
Yeah.
that 1/2? Like where?
Yeah.
So it's se 1/2.
Well, it's divided by 2, r squared.
Where is? Oh, is that
This is an
that
R.
an R?
Yes.
Thank you.
So we have this equation. We're not done. We have a constant. So what does constant indicate? Anybody? Free game. Toya and Anisha. What do we do? What do we need? Wonderful. Thank you, Anisha. So let's talk boundary conditions. In this system, we know there's always going to be some type of, let me get the picture. There's definitely some type of QR going on in here. There's simply some type of heat flow, because obviously at the center, we have this electric wire that's producing heat. So let me tell you, at R equals 0, what is QR?
Finite.
Wonderful. So we don't know the number. It has to be a number that makes sense. And it also can't be infinite. So it's just some number. Now, with that said, plug in your boundary conditions and you'll see something pretty beautiful going on. You'll get a number multiplied. This becomes 0 plus C1 over 0. Now, can C1 be anything but 0?
No.
No.
Right, because if not, it'll go to infinity, and QR is not equal to infinity, is equal to some solid number. So using logic and definition, C1 is equal to, say it with me now, 0. Now, QR is equal to SE.
Victor, go back for a second.
Yes, Malek?
I stopped paying. I got distracted, but okay, never mind. I know what you're doing.
You know what I'm doing?
Yeah.
Okay, you sure?
Yeah.
Okay. Right, so QR SCR divided by 2, and that plus C1 is gone. That divided by R is gone. Now let's talk about one of the things that I mentioned y'all should always have by heart. QR is full definition. That's a little too thick. Where is it? There you go, nice little thin black. QR is equal to negative K dt over dr. This is a definition that you guys should have like ingrained to your skulls. Heat is equal to this, no matter what we do. So guess what we do? We substitute the sucker in there. Let me go back to the wonderful blue. Negative K dt dr is equal to SC R over 2. Sonia, what do I do to solve this differential equation?
Do you have to do like separable variables or whatever? it's called?
No. Think even easier. I had Malak screaming to me last time. No? Watch
I
this.
mean, she's right. I mean,
Like you multiply
Now-
the dr over to the other side, then take the
yeah, she's right.
Oh, yeah.
It's like
Oh, yeah,
you're
yeah, yeah.
integrating by separation variables. Yeah.
Oh, okay. Yeah. That works. Integrate that shit.
Come on, professor.
I'm not a professor. I'm just a broke college student who needs money. K becomes KT equals SER squared. Remember, R squared over this R becomes R squared over 2. 2 times 2 equals 4 over 4 plus an integration constant C1. I want to point something out that I didn't realize. I skipped a step. Before you take your integral, do yourself a favor and make sure you divide this in here first. It'll make life easier. K, and there's a negative outside. So then there'll be a K here and a negative here. Do that before you take the integral. If not, this doesn't work. A little mistake there. I didn't follow my notes.
Wait, why wouldn't it work? I don't get it.
Because if you divide this afterwards, you have to divide it with the C1 too. Then it
Oh,
would be
okay.
this.
Okay, yeah.
Yeah. And it's disgusting. You don't want to do that. It's just not right. Sonia had a point, and you do the separation of variables and shit. I skip steps because I'm cool. All right. So we have this C1. How the fuck do we solve this? Right. So let's go back to our picture. What do we need? Boundary conditions, right? So we already used the boundary condition at r equals 0. So can anybody take a solid guess at what next the boundary condition is?
R.
All right, wonderful, Dominic. Who's next to be victim? What is R? So if you were looking at this picture, at R equals R, what is my temperature equal to?
Not.
T naught, wonderful, Anisha. T is equal to T naught. Using your brain. You see, it's all about staring at your picture and understanding what you're being given. And also memorizing these integration and memorizing these boundary conditions, because he reuses it. So at T equals T naught, we'll plug it in. T naught equals negative SE R squared, well, big R squared, over 4K1 plus C1. C1 then is equal to T naught plus SER squared over 4K1. The beauty to this is that you plug the C1 in here and you simplify. And I'm going to skip a lot of little steps that I think are relatively easy based on if you did the math with me last time. It's almost the same thing as a momentum balance. I just end up getting SER squared 4K1 1 minus R over R squared. This will now become our temperature distribution. Y'all remember how we used to get a velocity distribution? Doesn't that shit look damn near the same? Wonderful.
Yes.
And that's basically the setup to run through this whole thing to get your energy balance to work. But keep in mind, this is out of the simplest terms. We're only talking no flow. No flow makes things easy. Do you guys not like easy? I love easy. Everybody okay? On board?
Yeah.
Cool. I don't see faces and I don't see any like reactions, so that's why I'm asking. Okay. As before, if you have a system that abides by these conditions, you don't have a flow and you don't, there's no flow and there's some type of a heating going on, you can calculate the following things just using these basic equations. The max temperature rise is when R equals 0. So all happens is that you want to find the max in a similar sense. Ooh, just like before, you cancel this shit out and you're left with this at the bottom. How about your average temperature rise? Well, your average temperature rise is equal to 1/2 the max temperature rise. All of these equations should look relatively similar, and ring a bell to the last video, or if you were here in person, the last in-person lecture. There's just a pop temperature now. Now here's something that's kind of important. If they ask you, what is the heat flow outside the surface? You just copy this equation, and instead of SE, you would put in whatever that heat flow is, Q naught, whatever. But these equations stay valid. All right. So this is another example that's relative to the same. They have a different set of conditions. Here we have two types of fluids in a pipe. And these two types of fluids have two different types of temperatures, two different radiuses, and different boundary conditions each a pop. It's ran the same though. There's heat conduction with a nuclear heat source. So it's no longer an electrical wire. It's some type of, let's say, atom that's producing a bunch of nuclear energy. So let's
Oh
put
yeah,
the
I'm so
perspective-
sorry. I have a quick question. So what you just did with when you wrote it all out, that was just 10.2? Or that was
yeah.
yeah, that was 10.2. Okay, I just want to make sure because I was just looking at the notes and then okay, thank you.
So heat conduction of a nuclear wire. So let's say a nuclear heat source. You have two pipes. You have a pipe on the inside and a pipe on the outside, and they're surrounded by two different things inside of them. The inner pipe is this fish-locular, whatever the fuck material. And that's the one that has this heat, this nuclear source. The outside has aluminum catting, and then around it there's a coolant. So you would have to individually take the energy balance of the inside, this part, and the outside. The nice part about this all is that you can do this all using the most complicated one and then simplify for everything else. It's almost the same steps. So as before, we need to account by this nuclear energy in the viscous molecular thermal energy shit. And that is defined by S naught or SE or SN in this case equals to this arbitrary equation. As before, the equation here doesn't really fucking matter. What matters is that you take this shit into account because it's important for the balance. Now, they define what B is here as just a positive number that's dimensionless. You should be given this if you have to do it. And in the same vein of things, we take a slice of, or a shell of thickness, delta R, in the viscous material. Note, this is no flowing, so V is 0. And Q and thermal energy are the only things present. Literally the same thing as before. I'm not going to write this all out. The only difference is that this is a sphere. So the area of a sphere is no longer 2 pi RL. You just go to fancy Google, Control T, area of sphere, and you find out that it's 4 pi R squared. The beautiful part about it is that QR is the same because it's still a sphere, and there's no other surface. So all you got to worry about is the heat conduction at R. In a similar sense, the area doesn't change for either of them. QR, there's this arbitrary little F that's in parentheses. And the only reason I put that is because it's specifically talking about this center material, nothing else. So you have the same equation top and bottom, just R plus delta R and R. In a similar vein, now instead, we need to take into account the rate of thermal energy dispatched, or whatever you want to call it. The rate of energy by nuclear energy. So you're going to take that SC, that SN, or whatever the fuck they defined it as, and multiply it by the volume of your system. It's a sphere, it's no longer a cylinder. So it's going to be 4 pi R squared times delta R. Delta R being the thickness or the length and thickness of your arbitrary cylinder that you took a slice of. In the same way, we write the balance. Obviously, R minus delta R plus the area. You flip the signs like we did before, and you rewrite it, and you also divide by 4, delta R, and pi, and take the limit as R approaches 0, or delta R approaches 0.
Question.
Mm-hmm.
And the reason why we divide it by the 4 pi delta R is because of the S, like the SE part? Because you want
the reason
SE by...
You don't want it by itself. In cylinders, the horrible part about cylinders and the horrible part about spheres is that 9 times out of 10, you want to keep the R term alive.
Oh, okay. So even with the last question that we were looking at, we divided it by the delta R, or the delta R on the previous one as well, right?
Yes, but we didn't divide by R.
Correct. Okay.
And so following that same basic premise, you get your limit, you have R squared QR, you do the sign flip so it doesn't give you a negative derivative. Giving the sign flip makes this thing positive up in the exit. And look at that. It looks pretty much the same. Now, here's a couple things. It's pretty much the same, but this SN term is this disgusting thing right here. This derivative term here is R squared instead of just regular R. And that's pretty much where you want to stop. Like realistically in a problem, after that, it's just getting your boundary conditions and solving. Now, let's say I wasn't talking about the viscous material with all that disgusting thermal energy. And we were talking about this aluminum catting that doesn't have nuclear energy going. So what's the only difference? There's still heat transfer, but there's no nuclear energy being conducted. So your balance is exactly the same, but, big but here. The only difference would be that you don't have this term at all. And if you don't have that thermal energy term at all, what happens to this SE term? It doesn't exist. So then you'll be left with the same differential equation. Instead of equal this thermal energy, equal that shit to 0. Everybody okay?
Equal 0 again? I'm so sorry.
When there's no thermal energy being generated.
Oh, okay. Okay, so in the problem, they would probably be like, oh, there's no energy generated or something like that.
Well, they straight up just tell you it's only nuclear energy being conducted into fissionable material.
And so
Yep.
because of that, there is no energy. Okay.
There's nothing in the aluminum. Nothing's being conducted. Nothing's being made there.
Okay, okay.
Wonderful. So then we're going to solve our boundary conditions at R equals 0. QR is not infinite. Same logic that we used before. And does C1 equal to 0. The nice part about this is that we'll do a similar test here. The only difference is that we won't use temperature for our second boundary condition. Rather, we're going to use the picture for your boundary conditions for your second term. Well, if at R equals 0, QR is just some random ass number. At R equals, let's call this term RF for fissional material, Q is equal to QF. And that's the nice part. You just plug in your numbers, you solve it. It's a lot of integration. These just go through the math, same exact steps as before. Just get your boundary conditions right, and it'll poop out this thing in pink. All the interworks on the math isn't the important part. To me, if you can get here and you can name your boundary conditions, you already won. Everything after that is just algebra. Now for 10.4, this is a little bit more annoying because this problem becomes a little cracked up. And the reason it comes cracked up is now we're talking about heat conduction with a viscous heat source that's taken into account with the energy balance. So you don't have to worry about that SC or SN term. But the difference here is that we have two cylinders. One is the outside cylinder and one is the inside cylinder. The inside cylinder here is stationary, so it's not moving. The outside cylinder is moving constantly. It doesn't really matter in what direction, but she's moving. So between the cylinders, that causes a disgusting amount of energy to be produced, and we have to take that into account. So you're going to take a shell of the cylinder in this purple box. Wonderful. The outside temperature here is TB, and we're going to assume that temperature is only a function of R alone, which is good. So we'll take a shell of the purple box, and we'll get this picture right here. And we need to make a couple assumptions, and we'll talk about those in a second. For starters, that shell that we took is a box for a reason. We're going to pretend that we took a shell of the cylinder, but we can ignore the little curvature it would have. So those curvatures that you would see here, they're gone because we're purposely ignoring it. Next thing, we're going to talk about the temperature. The temperature at the surface is some arbitrary temperature that we'll label T naught. We don't know what the fuck it is, but it's T naught. At the exit, you know it's TB because the problem told you. Top is a moving surface, the bottom is a stationary. We'll label our directions. Going up is X, going to the left or going to the right is Z. And you can label the box's dimensions too. Lengthwise it's L and up and down it's W. So if we ignore the curves, we can now name our velocity distribution an arbitrary function of Vz because it's only flowing in the Z direction. Hence this velocity curve. Now, since we also said that this is a function of RB, the problem in the book just gives you the conversions to it. It says Vz equal to Vb at X divided by B, where Vb is equal to omega R, and that makes it a function of R, just like they want it to be. But that's not the important part. The important part for us is to make an energy balance. We're going to say that there's energy obviously being conducted up and down from the surface because there's Q here. Let me draw it. Obviously, there's energy being conducted this way, and there's energy being conducted here. The surface to the outside, this to the inside. We need to take that into account, and we already took the shell of it. We know where it's coming from. At X and X plus delta X. In a similar sense, we need to get the area of your surface. But remember, we made life easy on purpose. The area of our surface is a box. It's no disgusting cylinder, so it'll just be W multiplied by L for both in at X and in both at del plus delta X. So it's beautiful, and there's no heat generated on the inside. The trick to it, though, is that energy is no longer just Q. And the question is why? So we're saying it's no longer Q because now we have this cylinder that's moving. The top is moving consistently. The bottom is by itself. Due to that, it causes flow to be created in the direction. This movement creates flow. And the nice part about the last two problems was that if there's no flow, then half the energy equation goes to shit. In this case, there is flow, so those velocities matter. So we'll continue and pretend that nothing's going crazy, and we'll just keep Vx or Ex generally. In the same way, we take the inside minus the outside, we rearrange it to the outside minus the inside, and then divide by WL delta X. Now, Dominic, I hear your question already. Why do we divide by W and L? Because it's a box. You don't want to leave anything in front of these guys. So divide that shit the whole time. So divide by W, L, and delta X and rearrange. Ignore my little fuck up because I left W and L here, but they should be gone. Becomes the derivative of E of X equal to 0. In the beautiful words of Madeline, you take the integral of that shit and you figure out that EX is equal to C1. Now, we have to replace EX. And this is where the funsies happen. So EX is all of this in the X direction because we saw it going up, but there's flow. So here's the thing. Its first term, Vx, is 0 because we said the flow is only flowing in this V direction. So ignore this first term. Now, the issue with this term here, the tau times V, is that you go to the back of your book and you be real smart. You find the what this all equals. It's in my notes. You can go back and look at it. You have tau XX times Vx. There's no flow in the X direction. Get that shit out of here. Tau XY, Vy. There's no flow in the Y direction. So get that shit out of here. Tau XZ, Vz. Vz exists. We look at the picture above. Then it simplifies to tau XZ, Vz. Now, connect everything I said previously. What is tau equal to? Everybody here that was here last time should tell me shear. Shear has an equation that can be defined as tau equals negative viscosity times the derivative velocity, in this case, x dx. And so we just plug it in there, and we have that term that we're going to replace in the tau times v. Now Q is always there. Q, there has to be, there's an energy balance, it's being conducted. So Qx, easily replace it with the terms I talked about in chapter 9 with Fourier's law. It's right here. Now we sub in those values into the differential equation here, and we get everything being replaced. So we get this nice disgusting term in the front. We get this Fourier's law here. This becomes negative, the K is negative. This becomes negative because the mu is negative just based on the definitions. Now, since we have the book telling us specifically what Vz is equal to, the book just tells you it's equal to VB x divided by B. Plug it in there and simplify. So if you plug it in there, you can literally take the derivative of this function and it simplifies it to negative mu x VB divided by B squared. That's just a simple derivative. This part doesn't change because it stays negative dt dx equal to C1. Now, the book actually does something really dumb and doesn't explain too much, but they say, you know what? Integrate this shit one more time. And assuming you guys are good at math, you'll be able to get t equals this entire function at the bottom. All of this is arbitrary because as long as you can get to here, you copy this equation next. What's important here is you apply your boundary conditions. At x equals 0, what is the temperature? Well, it's just an arbitrary T naught because it's the surface temperature. That's what we're calling it. How about at x equals b or at x equals x plus delta x? Well, at the outside, we're saying that the arbitrary temperature of the outside, which was TB based on TB on the outside. We give the two boundary conditions and you integrate and solve. There's a lot of heavy lifting in there that you go in Wolfram or you just literally do anywhere else and don't waste your time doing it. You get this beautiful equation here. And they use a dimensionless number that's defined down here. None of that's too important, but what's important is that you understood the logic and steps to getting there. The actual hard work of math is not important. Everybody still following the boat?
Yeah.
Everybody else?
Yeah.
Okay. All right, 10.5. Now, heat conduction with a chemical heat source. This is a bitch. I don't like this at all, but we'll try to explain it. So imagine that you have this box that has 3 zones. Zone 1 is inerts, nothing's happening. Zone 2, there's catalyst particles and a reaction's happening. In zone 3, there's inert particles too. Now, zone 1 and zone 3 are boring. Screw those. We're talking about zone 2 specifically. And zone 2 is sandwiched in between Z equals 0 and Z equals L. And it's between 2 insulated walls, meaning the temperature barely changes. But in this case, because it's a chemical heat source, it's a reaction that we can model through a thermal energy. And this can be done by this arbitrary constant the book gives you that SC is equal to SC1 times the function of theta. And they tell you what theta is and it's dependent on temperature. That's not too important. But in a similar case, we got to take an energy balance of the system in zone 2. What's coming in, what's coming out. At Z equals Z, what's the system? Here, I guess this is a pipe, and so they do pi r squared multiplied by multiplied by energy, pi r multiplied by energy in, multiplied by the obviously volume of your system, and do the same exact steps. You get this thing to be a derivative in function of what am I dividing by Z equals SC. SC, as previously, was defined by the random function they gave you. In this case, they gave us SC equals F of theta. In a similar sense, in this case, there is flow, so we have to use the full energy equation. So this EZ becomes this 1/2 all of this shit here. You do through the same process we did last time. So this tau ZZ VZ will simplify to negative mu VZ DZ. This QZ simplifies into the Fourier's law. And since we're assuming constant temperature, constant pressure, CP, which the problem tells you, you can just make this rho del H even bigger. Here, the beautiful part about it is that if it's only in one direction, 1/2 rho V squared becomes 1/2 rho VZ squared multiplied, VC squared, excuse me, multiplied by this term right here, distributed. This rho H hat becomes rho CP times the difference in temperature times the VZ distributed, plus the difference in pressures multiplied by the VZ that was distributed, plus the original rho times H hat with the VZ distributed. Essentially, I didn't figure this out until recently. This term here will become all of these terms here. And in this VZ is just being multiplied to everything, which is why you see it here, 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 and here. Make sense? Wonderful. This Fourier's law just gets subbed into here. This is after you figure out your basic math and put it in here, the same way we did above. And we get to simplify these terms. The first, the fourth, and the fifth term go to 0. Since VZ is changing with respect to Z, so none of these matter. The third term goes to 0 because there's no del P. And the second term, we replace VZ with V naught because that's actually an important term. And this is disgusting, but you could go through the math. It should simplify to this for zone 2. And that's really where we should end this conversation, because for zone 3 and the other zones, the only difference is that you won't have this SC term. And they give you all these boundary conditions for every single term. I'm not going to go in depth because I don't understand it and I don't want to give you lies. They go through this dimensionless form. But what matters here is that they're able to solve it in this solution here. Zone 1, theta I, makes no sense. This, on the other hand, we'll move to 10.6, is going back into realms that I can explain. Yeah, give me a sec. Sorry. Heat conduction through a composite wall. So in the book, they go through this giant mission to derive this, but I'm going to tell you right now, don't derive shit. Just use this equation right here. A composite wall basically means that you have 3 different types of walls next to each other, and there's heat going through this wall in some way, somehow, some fashion. So it could be heat this way. But how do you account for all these different walls? Simple. You're going to use the temperature of the outside of the first wall versus the temperature of the outside of the second wall, TA versus TB. And you're going to use the difference between the energy it takes to transfer the heat between this wall and the surface, and the energy it takes between this wall and the outside surface too. That is accounted by 1 divided by H naught, and H naught is a heat transfer coefficient, which is just a value should be given. How about the heat transfer between these 2 walls? Well, that's going to count it by the thickness, so del Z, or del X, excuse me, divided by this K. And each K is unique to the walls. And then that'll get you this term right here in the middle. You just give everything and make sure everything's in order, make sure your numbers are nice and neat, you plug and chug and you get a nice little cube. How about in a different world where life isn't easy? Well, if they're asking for more, you can just say, you can write this simply as U times TA times minus TB. It's just this, and they're saying everything in the bottom, 1 over this is U. Not a big deal. If you want it in terms of joules per second and no meters, obviously just multiply by the area. Now for a cylinder, it's the same exact thing, except this is capital U, so it'll give you in joules per second. So 2 pi RL, that's the area. If you don't want it to be per second, if you want it to have per meters cubed, just take away the 2 pi L. And the same exact logic applies, but the only difference is that instead of just being H naught, you need to multiply by the radius for the top and bottom of the surface with the outside world. And instead of being del X, you're doing the natural log of the radiuses divided by the case. This is stuff that we should have seen in 302, assuming you didn't sleep through the class. I know I did. Where is it? There you go. And don't worry, we'll get something into the board real quick. I just want to get through all of this. So if you go into the 10.7s, the book does a terrible job explaining, but I've actually figured this out before while I was doing the homework. So if you don't want to go through the book and all the disgusting math, you go and Google heat loss per fin, watch Learning Chemi's video. They derive every single equation here, so it's all factual and evident. So important here is that the equation for heat loss is Q, capital Q, meaning it's per joule per second, is 2 pi L W times the heat transfer coefficient, difference between the temperature of the wall and the temperature of the air, multiplied by this thing right here, which we call an effectiveness. That effectiveness has an equation, which sucks, because if your calculator doesn't have hyperbolics, you're fucked. That effectiveness is equal to tangent H, which is hyperbolic sine of N divided by N. N is equal to H naught, which is heat transfer coefficient, times the length squared, times thermal conductivity, times B. B in the picture that I can pull up if you need to, if you want to see a reference, is the thickness divided by 2, which I note down here. 2B is the thickness from the figure 10.71, and it's the straight up thickness, but B is just half that thickness. Now, if they're asking you to estimate the temperature of a gas stream using of a fin, this is the equation for it. You should know the temperature of air, the temperature of the wall, and you could solve for T1. This is hyperbolic sine multiplied by 1 minus Z divided by L times N, which N is defined up here, divided by N. Solve for T1 and everything else is known. You go to your calculator, your Wolfram Alpha, whatever, and it'll solve it for you. Don't waste time doing this the analytical method. Okay, let me take another water break. I feel like I'm talking forever. All right, we're gonna take a little break. I'm gonna go use the bathroom. I'll be right back. I'm sorry, guys.
No worries.
So let me stop. I'll keep it sharing. I'll just do it here. I'll be back. I'm sorry, guys. All right, homies, how we doing? Everybody okay?
I'm here.
Wonderful. Everything making sense. I feel like I'm talking a lot, not hearing a lot of response.
I think it makes sense. It's like kind of like what you said. It's almost a little bit like a repeat of some things.
Yeah, that's the whole purpose of going into depth with it. I can't believe it's been damn near fucking an hour and I'm only talking about 10. Damn. You might actually have me talking for the next couple minutes. Let me see something. Tell you guys what. Let me see my notes real quick. I'm gonna decide what I want to do because I need to think of something. I want to see what's important enough to show you. Okay, yeah. We're gonna do 10.8. This is the last major section that it's very important for chapter 10. Then you guys can just use my notes for free convection. I don't think it's useful at all. 17 should go relatively quick. It's just a shit ton of definitions. And chapter 18 is going to be another big, thick one. So, is everybody okay with that?
Yeah.
Damn, I feel like you're the only one here, Tommy.
Yeah.
But, okay. Cool. Okay. Sorry about that little expo, guys. I need to figure out how to cut that out from YouTube. If not, they're gonna have to deal with me having used the bathroom. So unprofessional.
No worries.
Okay. Okay. So we're gonna talk about something so important that I think deserves to be really paid attention for two reasons. Forced convection is something so useful that I need everybody to pay attention to. If you can do forced convection, you can solve any fucking question that he gives you. Is everybody on board? Y'all better be ready.
Yeah.
Yes.
This and 10.2, the two most important sections of this whole fucking chapter. I'm just promising you, based on like a son's old exam, you can reverse engineer what he's asking. And he's asking a forced convection question, and he's asking one of the ones with the thermal energy. That's why I spent time on those. This is another important one. This is called forced convection. Now, forced convection basically means we have a fluid with flow, and it has physical properties of obviously dynamic viscosity, thermal viscosity, rho, and in Cp. We're going to assume all of those physical properties are equal to a constant. They don't change. And we also are going to assume laminar flow, which is basically the assumption we're going to do for everything. If it's not laminar, it's not Newtonian, it doesn't have constant properties, this shit doesn't work. So we're going to talk about flow in a pipe. So let's draw that pipe. So we're going to have a pipe in every fucking question, of course. Make sure you draw it prettier than mine. And in this pipe, it's going to be radius this way, Z down here. And we don't worry about the theta like we said a million times. We have flow. It's moving downwards. Now, as everything before, this is Vz equal to 0. This is Vz equal to L. as any good engineer is going to tell you, shit, this seems like a really similar problem we did last time together. Just based on looking at this, you need to remember one thing from section 2. Do you guys happen to remember the velocity distribution? VZ we already modeled before. We said VZ is equal to fancy rho, which Madeline screamed at me for calling a rho, divided by 4 mu L R squared 1 minus R over R squared. Now, I want you all big brains to remember a couple things. We already did this. Go back to the last video, and you can see me derive this equation. The reason we're using it, it's the same exact thing. There's fluid going down the pipe, R direction, left direction. Cool. That's not the exciting part of this, but we do need this in order to answer the question. The next part is, what's the first step in any?
Is that for, what is that for?
This is called the velocity distribution.
No. What,
section.
so under the division.
4
sorry.
mu L. 4 mu L.
Thank you.
Mhm.
Thank you, Malek. Okay. So, as any good engineer is going to tell you, let's take a goddamn shell of this system. Let's take our shell. Arbitrarily drew it super big. It doesn't really matter. You can take wherever you want. In that shell, it's going to be a little small cylinder.
Can I have a question? So you're just taking basically like, are you taking a slice or are you taking like
A slice.
So it's like a circle.
Yeah, well, it's still technically a cylinder, but yeah, it's the
So
slice.
like okay, I gotcha. So it's like
Makes
a
sense?
disc, like a disc.
Yeah, exactly. I like calling it slice. You and me understand it because it's Dominican, but the book calls it a shell.
Okay, so disc, got it.
So this disc has a radius r, and since we're taking the slice of it, we know that this and this is a distance of del L because it's a slice, because this is L, or excuse me, Z, and it is Z plus delta Z. In a similar sense, we know the difference between here, the middle, and the out. This would be R plus delta L, or delta R. Essentially, that boils down to this being delta R. Wonderful, wonderful, wonderful. Now, we need to talk about energy. And the reason this is important is that energy, obviously, here matters. We're not just talking about heat conduction. There's a velocity component. So therefore, we do have taus and we do have 1/2 rhos and v's to worry about. But for now, let's take the balance on our shell. The balance we need to talk about is the total energy balance at R, the total energy balance at R plus delta R, the total energy balance at Z, and the total energy balance at Z plus delta Z. Now, this gets a little complicated, but in theory, your area of every single pipe you ever take of, you don't have to worry. It'll be the same numbers for everything, I believe. If I'm looking at my thing correct, it is. Okay. So at R, you're going to say 2 pi R del R multiplied by E, that's an E, 2 pi R delta R, ER at R, and I made a little minor mistake that I caught because my handwriting's terrible. It should be a 2 pi R delta Z, because we're talking about the Z, that's the length in this case, ER at R delta R, you have 2 pi R delta Z times ER at R plus delta R. Wonderful. At Z, your area is basically the same. The only difference is that instead of that delta Z, guess what you put in there? A delta R multiplied by EZ at Z, Z plus delta Z becomes the same thing. Pi R del R times EZ at Z plus delta Z. Okay, so we have everything accounted in for the R and the Z direction. 2 questions for you. I mentioned this very importantly at the beginning. This is free game. Anybody can answer. I would like most people to take a shot at it, though. We need to take into account what? Is there any thermal dissipation or any thermal energy being produced?
Don't we need gravity because it's really down now?
Yes. Good job, Madeline. That's one part of it. So you already took the other question. But do we need to take into account any energy being produced? Yes or no?
No,
Okay. Why?
because thinking about it, there is no like wire or anything like that.
Fucking beautiful. Good. So
Also, I have a question. So for the Z plus delta Z, it's 2 pi R delta Z times ER, and then
Delta
it's the
R.
line. Or delta Z.
All right. So it's 2 pi R del R times EZ slash EZ plus delta Z. This is
Okay,
just one
perfect.
term.
Yeah. Perfect.
I just put the Z to define where they're at. And as Madeline and Dominic pointed out, there's no thermal dissipation, but there is gravity because gravity is affecting the fluid. Do the work. Gravity will define
Can I ask a
as
stupid question? Even though Dom already
more.
explained it, can you explain why there's no dissipation again? The thermal dissipation?
Yes. And it's not a stupid question. Here's how this works. In the previous problem, we said there was an electric cord producing energy. So there's thermal dissipation. And another question we said, thermal dissipation. What the hell did we say? Give me a sec. There's an electrical wire, so that made energy. And the other question, there was nuclear energy being created. So we had to have an SE term and an SN term. In this case, there's only fluid flow. And the question isn't about if this fluid is creating energy. It is, but we're taking that into account with the gravity and energy balance. There's no other material creating energy, though. Does that make sense?
Yeah, thank you.
Okay, wonderful. Sonia, Anisha, are you guys still here?
Yeah, that makes sense.
Cool. You're allowed to interrupt, Sonia. I know I sound like I just keep talking. Okay. As we were going, rho V, oh my God, my pen's doing that stupid shit. Rho VZ times gravity. That's like gamma, like in fucking 300 or whatever the fuck that shitty class was. Multiplied by the volume component of it, 2 pi R del Z. That's your gravity component. Now, you guys remember all the
Question. So
Answer.
I'm looking back at your notes where you're writing this down and it says rho VZ GZ. So do we have to
Right.
multiply by Z
So
too?
So, okay, since you're following along through the notes, let me explain that really quick. G is literally only dependent on gravity going downwards.
Okay,
has no
so
direction.
that's a subscript then. What you're
Yeah.
trying to say. Okay. Got it. And that's a rho, not an E, correct?
Correct, that's a row. That's a row.
Got it.
Am I free to continue, ma'am?
Yeah.
Okay, so as before, we're going to divide, and in this case, we're going to divide by 2 pi del R del Z. Remember, since we're talking about a pipe, you leave that R in front of everything, okay? So I'm gonna write it down. We're gonna divide everything by 2 pi del R del Z, and rearrange, in this case, we're not gonna rearrange it. I didn't write it rearranged, so we're gonna keep the negatives coming in. So don't rearrange it, we'll do it, and you'll see why we normally rearrange. R at R minus R at R plus del R divided by del R plus, I'm going to factor out an R because the same shit. I could have factored out an R here, but we're just going to do it this way.
Wait, so it's RER slash R, right?
Right.
Okay, and then it's minus RER slash R plus GR? Delta R.
Delta R.
Okay, thank you.
And this is going to be divided by del Z plus rho. Oh my God. I'll make them nice for Madeline. It's going to be. What the fuck? Give me a sec. My pen's giving me shit.
I have a quick question.
Yes, Anisha?
Is that supposed to be EZ Z plus delta R or delta Z?
Delta Z. Thank you, ma'am. And that looked like trash, but my head started going crazy. Okay. The last term is rho, VZ. You don't need, it's just gravity. You don't need the Z, but it's the same thing. Times R. Wonderful. And all of this is equal to what? Take a guess.
0,
Because
because that's the law. It's laminar.
Steady state.
let's go, Malak. Dominic,
that one.
you had the answer given to you. You couldn't do it.
I'm sorry.
that? So, Malak, what do these all look like to you?
Good old derivatives.
Fuck yeah. So we take the derivative or the limit of del R and del Z, and we take this shit to differential form. Now I want people to notice that I on purpose didn't flip the signs, and if we don't flip the signs, we get negatives. So you're gonna get negative, and this is the book. The book goes through everything. In this specific case, you're gonna get a 1 over R. I don't know why. It just happens to be there. dr. Oh, I actually do know why. Give me a second. I'm being stupid. R E R minus dz of ez plus rho vz g. You divide that R from this side, and it gets it to you nice and perfectly. Wonderful.
Are those E's or rows? All of them.
All of them are e's,
Okay.
except for this one. I'm sorry. I'm not used to writing my rows like that. Okay. Remember how we talked about in the momentum balance where we needed to replace momentum? We need to replace energy for every single one of these ER and EZ. So let's talk in steps. New page, because I like things clear and I like things big. ER is equal to tau R V Z plus QR. Right? So since there is flow in the Z direction, does this term exist, the tau R V Z? Not a trick question, boys and girls.
Wait, can you repeat that?
There is flow in this pipe, and it's coming down the
Oh, yeah, so that exists, yeah.
beautiful. And the beautiful part about this is that we can replace tau the same way we've done before. Negative mu dvz dr multiplied by vz plus qr. Obviously, QR exists because Q exists in every freaking thing you make. It never goes away. So Q's there, and what do we replace QR with? Fourier's law. Negative K dt dr. This term here will forever exist. So make sure you take into account. It never goes to 0. Let's talk about the EZ direction. Now this one is complicated. There is flow, and there's a lot of flow, and flow is disgusting. So if there's flow, it kind of fucks you over because it becomes a really complex looking thing, which we'll just shove in, and we'll explain why terms go away in a sec. Okay. No. I'm not used to writing it the way to differentiate them. Sorry, guys. Okay, let's play the game of things. Does a velocity in the direction exist? So all of these terms exist in some way. QR is Fourier's law, tau is Shear's law. Now, remember, this term, we'll leave it. This term, remember how we defined it as that disgusting ass rho rho CP delta T plus rho H hat plus rho. It's a long one. We went through it in the paper with the pressure differences. So we'll rewrite it all the way through. This becomes 1/2 rho VZ squared VZ plus rho, just a rho, I'm not replacing it, rho H hat dot VZ plus P minus P dot VZ plus rho CP del T. All of these are multiplied by VZ because we're distributing that sucker like we showed you before. Minus, if you go into the differential equation, not the differential equation, excuse me. If you go into the terms, you'll realize this simplifies to negative, excuse me. It's already a minus 2 mu dVz over dz multiplied by Vz minus Fourier's law, which is just k dt dz. Okay. So the book does me the favor, and it combines everything and it puts everything here. I'm going to show you the Reader's Digest version of it because I don't want to hurt your eyes with all of my distributing. So it becomes rho Cp hat Vz dt over v dt dz equals k, combines like terms, 1 over r d dr r dt dr plus rho squared, not rho, excuse me, the partial derivative in respects to z, we'll write that one like that, plus mu dvz dr, and this happens to be squared. It's just after combining a lot of like terms, plus vz negative 2, excuse me, the partial derivative of pressure with respect to z, plus mu 1 r. It's kind of nasty, but you'll see why it's not that bad. So if you go to your book and if you remember in lecture, anybody go to actual lecture? He mentioned this. I remember passing and hearing it because I was sort of paying attention that day, or at least trying. And the book explains it too. Basically, this whole term, 90% of the time is 0. So that saves you a lot of hassle already. It's exactly 0 in this case. And if you ever have a falling pipe, it's exactly 0. Don't even question it. Shit's just 0. Okay. We're going to choose to neglect this term. And the rationale for it is that force, and that force is so fucking small that it doesn't matter, per the book. Now, we're also going to ignore this pressure difference. It's also so small that we choose to ignore it. The specifications as to why are in the book, and he said it in a lecture. So no, you can simplify it. Now, we're left with this term, which we already defined on chapter 2. So rho Cp. And if we sub in that disgusting thing, we're going to get Vz 1 minus r over r squared dt dr equals k d dr r dt over dr. I just want to preface that if you get this far, you already won the game. If you get here, you passed. He's not going to tell you to take the differential equation to this, but he will ask you for boundary conditions. Now let's talk about boundary conditions. Remember our disgusting cylinder. At r equals 0, we can tell one thing. We know this pipe has a temperature. We don't know what the hell the temperature is, but we know it has a temperature. We all can agree with that, right? At r equals 0, T equals some arbitrary temperature. We'll name it T naught, but that's an arbitrary thing that I'm calling it. It's a finite number. Now let's talk about the outside. Looking back at the pipe, at R equals big R, which will be out here, the question doesn't tell us anything about H. It doesn't tell us that there's a liquid medium or a fluid medium having heat transfer. So we can obviously assume that R equals R, that k dt dr is just equal to q naught. There's no difference in temperature like previously. But let's say there was, let's just say for shits and giggles, this was surrounded by some green shit. If it was surrounded by green shit and it gave us H naught, you would write Q naught equals H naught T minus the temperature of the outside. But since there's no information on that, you immediately write this. Now, what about at Z equals 0? At Z equals 0, I forgot to write it in, but the temperature is given as T1. So that one's pretty self-explanatory. T equals T1. Now, that's all you need to know, and you would circle this, and you'd be like, okay, that's what I'm turning in. There's no way in shit he's going to make you solve that. That's just impossible. You have to go dimensionless. But yeah, that is forced convection. If you can do all of that shit, You're pretty much gonna pass this exam. Okay. Any questions?
No.
Let's continue. Give me a second. I don't have my mouse installed. Okay. We have chapter 17, and this is going to go relatively quick. So, chapter 17 is talking about fixed law of binary diffusion. In other words, the first section is like the first section of chapter 9. It'll tell us how to calculate this shit. So, here is its non-differential form, which is WAY over A equals density times the diffusivity constant multiplied by WA naught minus 0, which is just the mole fraction difference divided by the thickness. We all more usefully describe it as fixed law as a differential form, where JAY is the molecular mass flux, which A is the molecular species, Y is obviously the direction, minus rho DAB times the differential equation of mass flux, or excuse me, mass fraction. In a very general binary mixture, you can calculate the velocity of that said direction using the mass fraction multiplied by the velocity of that mass fraction, added with the other one, same exact way. Thus, you can simplify mass flux as JAY equals rho W multiplied by the velocity of the component. There's also a vector form of this. This should all seem really similar to what we talked about in chapter 9. Nothing crazy, nothing insane. Note, though, that if you're going to write for a species JB, the only difference is that instead of del WB, instead of del WA, it's del WB. And in the DAB, it's just flipped, BA. There's a bunch of dimensionless numbers here that you should definitely go in and look at. They nicely written it down. It is Prandtl, Schmitz, and Lewis. Nothing really crazy. You can go in the notes and find that. If you ever need to talk about pressure and temperature dependencies of diffusion for a binary nonpolar gas mixture at low densities, you can find DAB using this disgusting equation where I give you the parameters and the units of everything so you can plug and chug. For self-diffusivity of DAB, you can also use figure 17.21, where you can get the temperature, reduced temperature, and reduced pressure, and you can get a reduced diffusivity. And you can get the other component to it, which is the TC, which I forget what it's called. It's the same thing as TC and PC. The critical diffusivity using this equation. And then obviously you can solve for it relatively simple. Nothing crazy so far. This is a lot of just kind of useless shit, to be honest. The theory of diffusion, here's a bunch of equations you can use. I doubt you'll see any of this, but it's there in case you need it. I really don't think you'll ask. Theory of diffusion in binary liquids. This is where things get kind of annoying because they tell you, basically all of these sections have you a way to calculate diffusivity. You should just be given these numbers. But if not, here's all the conditions for it. Nothing crazy. I don't really think this section is important. I spent a lot of time reading it. It's just literally, if you have a polymer, use this equation. If you have a colloidal system, use this equation. Mass and molar transport by convection. Now things get a little interesting because these are kind of definitions you should know. 17.7 is the most important section. Here, everything we were talking about prior is from unit mass, but really we need to talk about molar units. Molar mass units are equation of motion. Molar units are for chemical reactions. 9 times out of 10, we're talking chemical reactions. We're chemical engineers. So basically, a mass concentration is the mass of species, whatever, divided by the volume of the solution. A molar concentration is the concentration or the number of moles of said species divided by the volume of that section. A mass fraction is just literally the total number, the partial number of mass divided by the total mass. Similarly, XA is just, partial XA divided by the total. In a similar sense, everything is the same, basically. Average mass velocity and an average molar velocity. You get V equals the summation of the mass fraction times the velocity. And in a similar sense, you get XA times the velocity of that said direction. It's V star because they call this they call it a different term, but it's still velocity. It's the same shit. Now, molecular mass, molecular flux. Molecular mass flux is JA P times the difference in velocity as shown as the first couple pages. Molecular molar flux is JA star. This is where molar shit happens. C times the difference in velocity. And here, similarly, they give it to you in mass units and mole units. and they simplify to WA or XA, which makes sense. It's nothing crazy. Now, here's where things get kind of important. Convective mass flux is this equation here, where it's just a lot of nothing, where it's rho times V equals rho V being velocity at the X direction, rho times V being the Y direction, rho times VZ in the Z direction. Similarly, you can write it for the molar flux of vector. Obviously, it's the concentrations multiplied by the velocity of set directions. Those deltas are just indicating IJK or direction. A summary, useful things to know basically, is that you should know the combined molar flux and the combined mass flux equations. They're written right here, J or JA star, or plus rho velocity, rho being mass, and then C being in molar. At this point, if you really think you want to know this stuff, don't waste your time reading it. Just print out table 17, 17.8/1, 17.8/2, 17.7/1, 17.7/2. It is much faster and easier to understand than my notes because they literally just show you what they are. That's not too important. Chapter 17 is a wash. I feel like I wasted time reading it. This is sadly where things get important. Again, we need to talk about chapter 18. Chapter 18 is a B.5. The reason for it is that we have one important equation that basically governs this whole thing. The combined flux equation, which is given by Na equals the diffusivity times the partial derivative of XA over Z plus XA NAZ plus NBZ. We're going to use the direction Z a lot. Get used to it. That is like your starting base equation. And essentially, it's a combined flux equals molecular flux plus convective flux. Equation 18.0/1. Now, it's actually easier to write a shell balance for this shit because we've gone through the really hard stuff. The rate of mass in minus the rate of mass out plus the rate of production of mass by A of a homogeneous reaction. If it's not homogeneous, it doesn't count as a rate of production. Okay, so boundary conditions are simple. If the concentration at the surface is specified, it's obviously going to be that concentration. If the mass flux at the surface can be specified, then you can make a ratio to, if the mass flux is specified at a surface, you can make a ratio correlating NBZ and NAZ. Pretty important to get rid of this NBZ term, because then you can actually use all of this equation in terms of A and not worry about NBZ. Now, diffusion happens at a solid surface in May at the solid surface A. A substance A is being lost to the surroundings. In a similar sense, it's sort of like it's sort of the same thing as Q equals H times the delta T. It's the same thing. You can model that using Na naught equals Kc times the difference in concentrations. It's the same idea. For the rate of chemical reaction is specified. If substance A is disappearing due to a first order reaction, you can model that first order reaction always as K1 double prime times Ca, which will come into play pretty soon. Okay. So 18.2 is talking about diffusion through a stagnant gas film. This stagnant gas film, you have certain liquid at the bottom. You have the gas stream of A plus B up here, but we're going to consider that this gas stream of A plus B is mostly pure B, meaning that most of the A is already gone or non-existent up here. So we have a constant temperature, constant pressure, gas A and B are ideal, which is important. We can also say that at Z equals Z1, XA is equal to XA1. At Z equals Z2, XA is equal to XA2. These are just moderately based on the picture. Now, assume only A is moving and B is basically stationary. If the problem tells you that B is stationary, you could automatically assume that NBZ is equal to 0. And then you can solve that top equation here without NABZ. And if you do that, the book is nice enough to give you the equation without you having to solve for it. It gives you this equation right here. Beautiful, nice and pretty. NAZ, that equation will vary depending on your circumstances. If it's stationary, use this one. If the component B is stationary, use this one. Let me specify. In a nice perfect world, you can always take a slice in a similar sense that we took a slice of our last component. Anywhere, we took our slice using this green line. This green line is sliced between the Z direction, up and down. It's coming in at Z and it's coming out at Z plus delta Z. Now, I don't know the volume of the surface. It's not like it really matters. So we're going to put an arbitrary volume as S. In a similar sense, that, not volume, excuse me, area. That arbitrary area is going to be multiplied by NAZ at Z minus of arbitrary area times NAZ at Z plus delta Z. And remember, the rules don't really change here. You already did hard work last chapter. So S is just a random cross-sectional area. Divide that whole thing by del S. And look at that. Del S times S, because you want to get rid of that S term in the beginning. And you get this nice limit, which everybody knows at this point becomes a derivative. If you don't flip the derivatives, if you don't flip the signs, then you get a negative derivative, which in molar world, you kind of want to keep the negative sign so you can get rid of it using the equation. So negative d dz naz, we define naz up here, which is negative this crap. So two negatives, if you plug it in here, make a positive. We're going to assume here a couple things. Since the question told us, or the problem statement, and you're going to be smart, you're going to assume ideal gas, this C can be modeled by PCRT. P and T are constants because pressure and temperature are just constants. Therefore, C is also a constant. So C can be divided out of here. So C divided by 0 is 0. DAB is dependent on composition, and both gas, for the composition for both gases are pretty much constant. So divide that term to the other side, and you're going to be left with DZ, or excuse me, DZ of all of this, just without the DA and C, equal to 0. Integrate this shit 2 times because you have 2 integrals. So the first is to respect to Z, and the other is also respect to Z. You'll end up getting this integration. Not too hard, not too shabby. This first part, just adding a lot of numbers. Now, things get kind of annoying because this chapter likes playing with your constants. Your constants are the most important thing in the world. Here specifically, they say, you know what? We're going to replace C1 with natural log or negative natural log of K1, and we're going to replace C2 with negative natural log of K2. And then we're going to simplify and apply boundary conditions, which we already stated for boundary conditions of X at Z equals Z1 was XA. And we said the boundary condition at Z2 was X equals XA2. Solving with these two combined, you get this equation. There's a lot of math in between that I don't really think you need to care about. As long as you know that this equation poops out eventually, that's what matters. Now, for average concentration of B between Z1 and Z2, you should use this equation that's written up here. XB average is equal to the difference in the concentrations divided by the natural log of the concentrations of B. The rate, this is an important equation, the rate of mass transfer, the rate of evaporation. If you ever get asked for the rate of evaporation, you immediately know to use this equation, NAZ equals to all of this. The nice part here is that if you go through the homework and if you don't have this, I know I went through this with Malak, this equation can be derived into something else, which I can send notes on that if you ever need it. So let me know if you want those. 18.3, diffusion through a heterogeneous chemical reaction. Okay, this is important. Remember, this equation says homogeneous reaction. So it doesn't apply to the shell balance, which is kind of nice. But let's paint the picture for you. You have a homogeneous chemical reaction. We have a catalytic surface where 2A turns to B instantaneously and irreversibly. The top is the edge of a stagnant gas film, so diffusion is going to happen through that. And it's coming through A, and B is going up. You have nice set to picture. At the top is equals 0. At the bottom is equals a random number. We don't know the length. You have XA and XB going through the surface. At the top, you have XB. At the bottom, you have XB2. Top, you have XA. At the bottom, you have XA2. We want to get an expression for the local rate of conversion from A to B with the effective gas film thickness and maintain concentrations of XA naught and XB naught that are known. We're going to assume this shit's catalytic reactor and it's isothermal. So there's a couple things we can do. We need to get rid of that NBZ term. First thing you want to do in most problems is get rid of that shit. So you can go to this equation that they're giving you, 2A yields B, and you'll realize that based on stoichiometry, we know that if 1 mole of B is moving in the minus Z direction, in other words, coming backwards, then you're going to have 2 moles of A moving in the positive Z direction, which makes logical sense if you just look at this equation right here. 2 moles of A are going this way, 1 mole of B is going that way. With that said, you can now then say, at the stationary state, NBZ is equal to negative 1/2 AZ. And then we can go back into equation 18.01 and solve for NAZ, and you end up getting this equation, which is given in the book. So you'll have to derive this if they don't use something like this, but basically just use the chemical equation and you'll simplify for NAZ, and you can get something somewhat here. Now you have to do another species balance like before, and the same thing, and same logic applies for your species balance. Take a random slice, you realize that there's a random NAZ And then there's also a random NaZ at Z plus delta Z. And we're going to arbitrarily name the reactor volume S. Doesn't really matter. It's the same exact thing we did before. The only difference actually is going to be the NA. The only difference actually will be this NaZ term that we plug in to this equation. In a similar sense, we're going to divide by dA, B, and C. So we get those shits outside, assuming they're constant. And then integrate this shit 2 times and do that replacement with the natural logs again. Apply boundary conditions. And since we're smart, intelligent beings, we already know them because it's Z equals 0, XA is equal to XA naught. At Z equals the length, or in this case, delta, which I named it, XA naught is equal to 0 because all of it's used up. And if you simplify and solve that equation, you get this beautiful number here. And they're nice enough to give us the concentration profile in the gas film, so you don't have to actually solve for it. You just use this equation. Now, here's where things get kind of spicy. And by spicy, we have a homogeneous chemical reaction, which makes things hard. It's not too much harder, but it is hard. So we're going to have gas A at top and liquid B at the bottom. In a similar sense, gas A goes and diffuses into gas liquid B. So it's the opposite of what we did originally. In the first question, we had B going into A. Now we have A coming into B. It's the opposite. It diffuses and it's irreversible first order homogeneous reaction that takes places. It looks like this. A plus B yields AB. We'll treat this as a binary system, ignoring the fact that AB exists because it's really small. So in a similar sense, we're going to take a shell balance of this green line, what's coming in, what's coming out, and we're going to assume S for the surface area because we don't know what the fuck it is. So NaZ times S minus NaZ at Z plus delta at Z times S. Now here's the difference. This is a homogeneous reaction. So we're going to add Ra, just like we did in Dr. Taymor's class, because Dr. Taymor showed us that Ra is the rate of reaction of a homogeneous reaction, multiplied by the volume of the system, which is del S times del Z equals 0. In a similar sense, we also remember that the book told us nicely that Ra is equal to negative K1 double prime times Ca, which is the same thing as saying that we can replace this Ra with this Ra value down here, divide by S, take the limit, and you get negative dz of NaZ plus the reactor reaction equals 0. Since the concentration of A is really small, it's basically a good approximation to assume that NBZ doesn't exist. So we can drop that term and just put everything into concentrations, where it becomes NaZ equals negative dBA dCA dZ. Plug both in this equation and Ra into this equation right here. We're going to get all of this nasty stuff here. You're going to get a dCA squared divided by dZ, because this derivative will distribute. This just gets replaced with this term up here, as you can see. And you apply boundary conditions at Z equals 0, Ca equals Ca naught, which is just logical. At Z equals L, you're going to assume this reaction goes all the way forward and there is no more diffusion at the wall. So boom, apply these conditions to this, and there's actually a way to solve it. You use the back of the book, or you just use the answer here, and you get this. It's disgusting. A lot of the math in this section is actually abominable. I don't like it at all because it's almost impossible to do by hand. So I really am banking on the fact that he won't make us do this because it's fucking disgusting. Okay. The average concentration in the liquid phase is given by this equation here, which is the average concentration divided by the initial concentration equals hyperbolic sine or hyperbolic tangent times phi divided by phi. This phi isn't momentum. It's actually this phi is equal to this square root of K1 times L divided by DAB. And if they're asking for the molar flux at the beginning of the system, here's the equation, and phi is the same as above. Ugh. Excuse me. Now this one is like a combination of everything you hate the most, because it's diffusion to falling film liquid gas absorption. So there's one good thing about it being a falling liquid. We already know that if it's going down in the Z direction, we already modeled this shit in chapter 2, which is this. This looks very familiar. And since the box, we don't have R, we have X divided by thickness. So we already solved the momentum balance. See section 2.2 in chapter 2 or the previous video. Now we're going to define this box. This box is a width W, this with W here, the length L. You have a starting place here and here. Now we're going to say this falling film liquid has two areas that shit can be absorbed. This del X section has a film. This del Z section is another film. These films happen to have moments of diffusion. To make life easy, the question says, you know what? We're just going to focus here on this specific section where we have del X and then del Z while there's flow going downwards. This section is the shell you're going to take. So you make a mass balance on that specific shell. And I'm not too exactly sure where they get this, but if you ever have something like this, I just copy what the book says. You take the balance, and this first section makes sense. There's a movement in the Z direction, and there's movement in the Z plus delta Z direction. Logical. And they're saying that it's W, the width, multiplied by del X as your area. And then they have the X and X plus delta X terms. And the things that don't make sense to me personally are the W. Like, I don't get where this W is coming from since it's not in this little small circle. But if they want to say it is, it is. So it'll be W times delta Z and W times delta Z for those. In a similar sense, everything works the same as before. You have W, delta X, delta Z, and you take the limit. You divide by those terms and take the limit. You get these nice differential equations. You plug in NAZ and NAX. So here in this case, since NAZ is literally moving mainly downwards, you can assume that it's mainly convection because most of the work happening there is in the velocity. So this first term goes away. And it simplifies to XA NAZ plus NBZ, which is the same thing as saying this term right here, which we discovered in class was CA VZX, basically saying that most of our actual work happens because of velocity. Now, since in the X direction, there is no velocity, most of our work happens per diffusion. So you have negative DAB, DCA, DZ. There's no velocity there, so it has to be the other term. You plug those suckers in, and you also plug in VZ, and you manage to solve this disgusting differential equation, and it simplifies into this with these boundary conditions. And they go through a really, 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 really long amount of work to get an error function, which to this day, I don't know what it means. But more importantly, they get a local mass flow of A, and it's calculated through this. You have a total mass of A, which will be absorbed, which is calculated through this. These two equations are really useful. If you did the homework, like legitimately try figuring it out, you just use these equations as R. Now, they also go through an entire different section where it's diffusion in a falling liquid film. It's called solid dissolution. The math makes no sense to Victor. I have failed you guys, big sad face. And here it is if you want to look at it. A lot of this section is kind of hard for me. But section 18.7 is diffusion of a chemical reaction inside a porous catalyst. So a porous catalyst is a bunch of little catalyst pellets, and we'll specifically take a look at one catalyst pellet. This one catalyst pellet has a stream of gas Ca and Cb going around it, as a concentration of CaR, and there's a reaction going inside the catalyst. It's A to B. Start making by your balance of a single particle. You're assuming the single particle is a sphere, so 4 pi r is your area. Makes sense. Multiplied by NAZ at Z, because this is the R, up and down is Z, and the same thing, plus reaction, because a reaction in a catalyst happens, which is the first order reaction here. Same logic as before, divide everything except for R and R squared, because it's the R, and you get the limit, take that sucker, becomes a differential equation, take the double integral, make sure you replace, after you take the integral, make sure you plug in your NAZ, or in this case, NAR. You get this disgusting thing, apply your boundary conditions, and you solve with a lot of math. And I mean a lot, you go in that section of the book, and I hope you can figure that out. The rest isn't really important, never mentioned in class, and that's pretty much our lecture for tonight.
Question.
Mm-hmm.
So you remember when the professor, he was like, oh, all of the like indoor in the book questions, can't think of the word right now, like the questions that we have for homework that are like not from the book, he says that those are old exam questions. Do you ever think you'd be able to just go through those and like maybe Sunday or Saturday or something?
I can't promise anything.
No, I was just curious because it's like obviously he has the solutions on the on the I can't think of the word on
Oh, if they're on
Blackboard.
there, then download them and go through them, boy, because I can't make you a promise for that. I'm
No,
sorry,
that's fair. No, I was just curious. But cool. Thank you, Victor.
Anybody else?
Please let me know when you post this because this time I was just listening to you. Now and like watching. Now
Dominic, this is a damn near 2-hour thing, so it'll take a while to post, but I'll let you know.
yeah, no, whenever. Thank you.
Okay, cool. I'm gonna stop recording then.